Hello and welcome to Unit 2, Chemistry, Matter, and Life. Today we're going to be getting into a little bit about chemistry and matter and how it relates to biology and life. And therefore this is an important fundamental unit because throughout this course we will be discussing various aspects of chemistry and how it relates to biology. To start off into chemistry, we need to discuss the structure of an atom because it is the building block of all chemicals. And so, looking at an atom, it has this basic structure where we have a nucleus at the center of the atom, and then we have an inner shell and a second shell, a third or outer shells beyond that. And each of those shells is where we find a portion of the atom. Taking a closer look here, what we can see is that there are three main parts to the atom. And so in the nucleus we find protons and neutrons. These portions of the atom have positive and neutral charge, as the names kind of allude to. And then in those outer shells that we just mentioned a moment ago, we find electrons that have a negative charge. Those electrons move around within those orbitals, and as they move around, they play a role when atoms come together in terms of chemical reactions. The analogy that you often hear made is that it's similar to a solar system where the sun is analogous to the nucleus, and then moving around the sun we have the planets. And so within the nucleus of the atom we have the protons that are positively charged, neutrons that have no charge, and then the planet analogy here are the electrons that are negatively charged moving around in the orbits. So the periodic table of the elements includes all known to man, at least, elements that exist. The elements are different from each other based on a few things we'll look at in a moment, but each of these are different types of atoms. Let's zoom in on one that will come up often in this course: sodium. Sodium on the periodic table has the symbol Na. And then we have a couple other numbers here. We have the 11, which is the atomic number for sodium. It is the 11th element in the periodic table. And then we have this 22.990, which is the atomic mass of sodium. And so what do these numbers represent? So here's an atom of sodium. And what we're showing here is that in the nucleus of the atom of sodium, there are 11 protons and 12 neutrons. And if you count them up, there are actually 11 electrons as well. Notice the number 11 comes up, and 11 is the atomic number, as we mentioned before. So the atomic number of 11 actually represents that sodium has 11 protons in its nucleus. All the elements of the periodic table have different mass numbers, and those mass numbers indicate that they all have a different number of protons. As you read along the periodic table, each element has one more proton in its nucleus than the last element did. For sodium, it has 11 electrons as well. And so all of the elements of the periodic table are all neutral. Whatever number of protons they have an equal number of electrons. So in the case of sodium, 11 protons and 11 neutrons. There are 11 positive charges, 11 negative charges, and the sodium has no overall charge. Looking at the atomic mass of 22.990, there's a bit more to this than we're actually going to get into in this class. But if we look at the number of protons at 11 protons and the number of neutrons at 12, we can see that those sum up to 23. And so the total there of 22.990 is can be rounded up to 23. And so this is not completely accurate, again, for reasons we won't get into in this course. But the atomic number for the elements is the sum of the number of protons and number of neutrons in the nucleus. Okay, so now we want to start talking about compounds and bonds that occur between atoms in order to create compounds. And so if we look at the sodium here, as we said, we have 11 protons and 11 electrons. The overall sodium is neutral, but if we look at the image here, we can see that all the 11 protons are contained in the nucleus along with the neutrons, and the electrons are found within these orbitals that we mentioned earlier on. But notice the outermost, the 11th electron in this sodium atom. It is out all by itself in the outermost shell of this atom. And so this gives a sort of instability to this sodium atom because electrons don't like to be by themselves. And so as we can see from the orbitals that are beneath this outer orbital, we can see the innermost has 2 electrons. And in fact, that means that this orbital is satisfied. It has 2 electrons, they're paired, and so it is full. And then we have the second orbital actually has 8 electrons in it. So even though there are more than the first orbital, with 8 electrons, the orbital is actually full. And so there's a level of, if you will, satisfaction in terms of that orbital being full. But the outermost only has 1 electron. It either wants to be full with 8 or it will want to give up that 1 electron. So the outermost orbital will be the second level. If we look at another element here, chlorine, this chlorine atom, it is the 17th element on the periodic table, has 17 protons, and it has 18 neutrons. It has 17 electrons as well to, again, balance out the number of protons. But if we look at the orbitals here, we have 2 electrons, a full inner orbital. We have 8 electrons in the second orbital, so it is full. But then we have 7 electrons in the outermost orbital. The chlorine atom is not satisfied in terms of having a full outer orbital. It wants to have 8 electrons, a full outer orbital, in order to be more stable. So here we have a situation where sodium wants to get rid of 1 electron, and the chlorine atom wants to gain 1 electron. And so what happens if we are in the lab and we take sodium and react it with chlorine is the 1 electron from sodium will move over to the chlorine atom, satisfying both atoms' need to have a full outer orbital. What ends up happening is we form a sodium ion. The sodium ion has a 1 plus charge because in losing the negatively charged electron, we now have an imbalance where we have 11 positive protons in the nucleus, but we have only 10 electrons outside of the nucleus in the orbitals. For the chlorine, we formed a chloride ion. And so we have that change in the end of the name for the chloride as opposed to chlorine. But it is an ion because it has 17 protons in the nucleus, but it now has 18 electrons out in the outer orbitals, even though the orbitals are all full and the atom is now satisfied and formed the chloride ion. The sodium ion and the chloride ion are a 1 plus charge and a 1 minus charge. And so what happens, the sodium and the chloride ions are actually attracted to each other because, as you've probably heard before, opposites attract, and so the positive charge is attracted towards the negative charge. And this ultimately is how we form sodium chloride, or table salt. It's the reaction between a sodium atom and a chlorine atom to form a sodium ion and a chloride ion, thus forming the bond between the sodium and the chloride. This type of bond is actually called an ionic bond. As the name implies, it's because we have this reaction between the 2 ions that form a full positive or negative charge. Another type of bond that we can form is a covalent bond. Let's look here at the oxygen atom. As you can see in the nucleus, we have 8 protons and 8 neutrons, and therefore we have 8 electrons out in the orbitals surrounding the nucleus. However, the outermost orbital has only 6 electrons, and so it is not full, it is not satisfied, and it requires 2 more electrons in order to be so. And so, let's look at some hydrogen atoms. The hydrogen atom is the simplest atom. It has 1 proton in its nucleus and 1 electron in its outermost orbital. However, the orbital 1 wants to have 2 electrons in order to be satisfied. And so we could have, if we looked at the ionic situation, perhaps the electron be given up by the hydrogen atom to the oxygen, but then we would just have 1 proton left over, no electrons. And so we actually have a different situation here. We form what are called covalent bonds. What actually happens can be seen in this reaction here, where instead of completely giving up the electrons from one atom to the other, there's actually a sharing of the electrons between the atoms. If we look at hydrogen in this case, there's the 1 electron from the hydrogen itself, and then there's 1 of the electrons from the oxygen being shared with it. And so the hydrogen has 2 electrons in its orbital. The same is the case for the other atom of hydrogen, And because of the sharing of the electrons from each of the hydrogen ions, if we look at the oxygen now, we can see that there are actually 8 electrons in the outermost orbital of the oxygen atom. And so, because of this sharing, all of the atoms are actually being satisfied in terms of having full outer shells. However, this is a covalent bond, a sharing bond between the different atoms that are involved in the bond. Let's get rid of some of the detail of this reaction here. Here we are looking at the exact same reaction. We'll move it off to the side to try to relate this idea of ionic and covalent bonds to the next learning outcome, which is to differentiate between compounds and molecules. What we're looking at here are ultimately compounds because they're made up of multiple atoms. But when we have a compound that is created from covalent bonds specifically, we call these compounds molecules. And so we're looking at the water molecule in part C here, but just above it in part B we can see a hydrogen molecule. The exact same logic that we've just looked at in terms of we have 2 hydrogen atoms, each unsatisfied with its 1 electron in its outer shell, will combine to form a hydrogen molecule through this covalent bond that shares the 2 electrons of that outermost level. Another reaction is here between 2 oxygen atoms. Both are unsatisfied with the outermost level of 6 electrons, and so these 2 oxygen atoms will form a covalent bond where they actually share 4 electrons, 2 from each atom, in order to form an oxygen molecule, O2. This is a molecule that we'll look at throughout this course because it's important for cell life, for respiration, and so on, other items that we'll talk about later on in the class. These are all molecules because they have covalent bonds. Other compounds are ionic compounds, and we've looked at those earlier as well because we talked about the sodium atom and the chlorine atom becoming the sodium ion and the chloride ion through the gain and loss of electrons. We form sodium chloride, which is an ionic compound, which we do not call a molecule, and so this is the difference between the compounds and molecules.